Scientists just broke a record that could change how we see the universe forever. Using the Chinese quantum satellite Micius, they managed to link particles, photons, across a mind-boggling distance of over 12,200 kilometers. These particles became entangled, meaning they influenced each other instantly, even though they were separated by vast space. This isn't just a cool experiment. It's a glimpse into how the universe might be woven together by quantum threads. Albert Einstein called entanglement spooky action at a distance, dismissing it as impossible. But this experiment proves that entanglement is real and works exactly as quantum physics predicts. Imagine pulling a string on Earth and instantly feeling a tug on Mars with no delay. That's quantum entanglement in action, a phenomenon so strange that it challenges the very idea of space and time as we know them. But why does this matter for space exploration? This discovery could lead to unhackable quantum communication systems, capable of connecting Earth with future Mars colonies or distant spacecraft with data transfers that are secure and instantaneous. And on a deeper level, it hints that space might not be empty at all. Hidden quantum connections could stretch across the universe, linking distant galaxies and stars in ways we're just beginning to understand. At its heart, quantum mechanics is about understanding how particles behave at the smallest scales. Electrons, photons, even atoms. Unlike the predictable rules of classical physics, the quantum world is strange and unpredictable. Particles can exist in multiple states at once, make decisions when observed, and, through entanglement, influence each other across huge distances. This quantum strangeness isn't just a lab curiosity. It's the engine behind the cosmos. Stars shine because of quantum tunneling, a process that lets particles pass through barriers they normally couldn't, making fusion in the sun possible. Without it, there'd be no sunlight, no energy, no life. Now, scientists are looking at how quantum mechanics might explain mysteries far beyond our solar system. Could quantum entanglement help us understand black holes, where space and time warp beyond recognition? Could it be the key to unraveling the secrets of dark matter or the idea that our universe might be a hologram? The Micius experiment is just the beginning of this journey. With each new discovery, we're peeling back layers of reality, revealing a universe connected in ways we're only starting to imagine. And who knows, the next breakthrough might not just change how we see the cosmos. It might redefine reality itself. Quantum origin of black holes. Scientists investigating black holes have uncovered fascinating insights into their quantum origins. A groundbreaking study proposed that some primordial black holes, formed in the turbulent moments following the Big Bang, may carry quantum chromodynamic properties. This theory suggests that these black holes might exhibit traits influenced by the forces that bind quarks and gluons, implying that black holes are not just astrophysical objects but are also deeply tied to the quantum fields that govern the universe. These discoveries are closely linked to Hawking radiation, a crucial idea in theoretical physics. This concept posits that quantum fluctuations near a black hole's event horizon create pairs of particles. One escapes into space, emitting energy, while the other falls into the black hole, gradually reducing its mass. While detecting this radiation remains a significant challenge, advances in experimental techniques offer hope. One key approach involves simulating event horizons in laboratories using ultra-cold atoms. By recreating space-time curvature, researchers have observed effects resembling Hawking radiation, suggesting that its cosmic version might one day be measurable. Another breakthrough comes from analyzing the universe's oldest light, the cosmic microwave background. This ancient radiation carries subtle anomalies that may point to primordial black holes believed to have originated from quantum fluctuations during the inflationary period. These patterns indicate how vacuum fluctuations could create structures that shape the universe on vast scales, connecting quantum phenomena with the formation of cosmic features. Adding to this, powerful telescopes have revealed an unexpectedly high number of massive black holes in the early universe. Observations show a surprising abundance of these objects within the first billion years after the Big Bang. This finding challenges traditional theories of black hole growth and suggests that some may have formed from quantum phenomena rather than solely through the collapse of massive stars. One explanation is that primordial black holes arose from the collapse of high-density quantum fluctuations, bypassing the usual star-to-black hole pathway. These primordial black holes could act as the seeds around which galaxies form, bridging the gap between quantum mechanics and cosmic evolution. Another experiment exploring the quantum nature of black holes involved analyzing gravitational waves detected by observatories like LIGO and Virgo. These waves carry information about black hole mergers. Recent data revealed subtle patterns that might hint at quantum corrections to the space-time fabric around merging black holes. These patterns could reflect phenomena such as quantum tunneling or fluctuations near event horizons, offering glimpses into the quantum gravitational interplay at cosmic scales. The theoretical study of vacuum polarization adds another layer to this understanding. Near a black hole's event horizon, intense gravitational forces warp the quantum vacuum, leading to the creation of virtual particle pairs. Experiments recreating similar conditions in particle accelerators have observed analogous effects, strengthening the idea that quantum fields play an active role in black hole physics. Such studies could eventually reveal how black holes interact with their surroundings, from swallowing matter to altering the behavior of spacetime itself. Another remarkable insight emerged from studies of gamma-ray bursts. These fleeting yet powerful emissions, often associated with black hole formation, might also signal the evaporation of primordial black holes. Theoretical models suggest that as a black hole shrinks due to Hawking radiation, its final moments release a burst of energy, detectable as gamma rays. Observatories like the Fermi telescope have been scanning the skies for such signals, hoping to confirm this long-predicted phenomenon. Moreover, scientists investigating quantum remnants left by evaporated black holes proposed that these could serve as cosmic memory banks. These remnants, though minuscule, might store information about the quantum states that formed them. This idea challenges the traditional view of black holes as obliterating all information that crosses their event horizons, providing a potential resolution to the black hole information paradox. Experimental efforts to identify such remnants focus on their gravitational signatures, which could be detected in the patterns of galaxy clustering or through microlensing events where light from distant stars bends around them. Primordial black holes might also hold the key to understanding dark matter. Some theories suggest that small black holes formed in the early universe could constitute a significant portion of this mysterious substance. Observations of gravitational lensing, where light bends around invisible masses, have hinted at the presence of such black holes. The European Space Agency's Gaia mission, which maps the positions of stars with unprecedented precision, has provided data that could uncover the gravitational effects of these elusive objects. The interplay between quantum fluctuations and cosmic evolution continues to astonish scientists. During inflation, the rapid expansion of spacetime amplified tiny quantum disturbances into large-scale structures. These fluctuations created gravitational wells that later collapsed into black holes or seeded the growth of galaxies. This process underscores how the smallest scales of nature can influence the largest, binding quantum mechanics and cosmology in a unified narrative. The study of black holes as quantum objects remains a frontier of discovery. Each experiment, observation, and theory contributes a piece to the puzzle, pushing the boundaries of what we know about the universe. From the quantum fields surrounding black holes to the ripples in spacetime they generate, these enigmatic entities offer a glimpse into a deeper, more connected understanding of reality. As technology advances and experiments grow more precise, the quantum origins of black holes may reveal truths that fundamentally reshape our perception of the universe. The quantum Big Bang. Cosmos researchers recently made a groundbreaking leap by using hyperbolic lattices to simulate the quantum states present during the universe's earliest moments. This innovative approach explored how conformal field theories, which describe quantum systems with intricate and symmetrical properties, could recreate the extreme conditions right after the Big Bang. By utilizing hyperbolic lattices, scientists developed a framework to better understand how quantum mechanics influence the fabric of spacetime during those critical moments. This research paves the way to unraveling how the quantum realm governed the inflationary expansion that shaped the cosmos. A particularly intriguing aspect of this study is its ability to connect tiny quantum fluctuations to the massive structures we observe today. During inflation, quantum mechanics suggests that even the smallest energy disturbances could stretch to vast scales due to the rapid expansion of space. These disturbances formed dense pockets, becoming the seeds of galaxy clusters. By simulating these dynamics on hyperbolic lattices, researchers added remarkable accuracy to our understanding, bringing us closer to bridging theoretical quantum physics with the observable universe. Further supporting this exploration, scientists have recently uncovered potential traces of primordial gravitational waves. These waves, born from quantum events during inflation, represent subtle ripples in spacetime caused by the stretching of quantum fluctuations. Detecting them involves highly sensitive instruments designed to capture faint distortions in ancient light from the early universe. These gravitational waves are a direct imprint of quantum mechanics, offering a glimpse into how microscopic quantum processes helped form the vast, complex structures of the cosmos. The role of quantum entanglement in the universe's early days is another area of intense study. Entanglement could have allowed particles separated by vast distances to share information instantly, influencing how energy and matter were distributed after the Big Bang. Recent experiments have demonstrated that quantum entanglement can persist under extreme conditions, similar to those shortly after the Big Bang. These findings suggest that entanglement may have helped stabilize the universe's structure during its rapid expansion, a concept still under investigation. The cosmic microwave background, or the faint light remaining from the early universe, provides further clues. New analyses of this radiation have revealed tiny anomalies that align with predictions about quantum fluctuations. The patterns in this background radiation indicate that quantum processes during inflation left a lasting imprint. These insights highlight the interplay between quantum mechanics and the forces shaping the cosmos, making the connection between the smallest quantum scales and the universe's vastness clearer than ever before. Another recent advance involves recreating conditions of the early universe using particle accelerators. These machines smash particles together at nearly the speed of light, mimicking the extreme energies present during the Big Bang. In such experiments, scientists have observed behaviors consistent with theories of quantum gravity, where quantum mechanics and general relativity converge. These studies shed light on how quantum forces might have dominated during the universe's infancy, offering a glimpse into physics beyond our current understanding. The study of quantum mechanics and the Big Bang also brings us closer to addressing one of physics' most profound mysteries. What happened before the Big Bang? Theories such as quantum loop cosmology suggest that the Big Bang was not the absolute beginning but a transition from a previous state. This idea posits that quantum effects could have prevented the universe from collapsing into a singularity, instead creating a bounce that led to the expansion we observe today. Experimental evidence supporting these theories remains elusive, but advances in quantum simulations and gravitational wave detectors might one day confirm or refute this possibility. Gravitational wave research has recently provided hints about conditions during inflation. By analyzing the polarization patterns in ancient light, scientists have detected signals consistent with gravitational waves generated by quantum fluctuations. These findings not only validate aspects of inflation theory but also demonstrate how quantum events leave observable traces in the universe's evolution. Quantum mechanics also challenges our understanding of time and space near the Big Bang. The fabric of spacetime likely behaved differently with quantum effects dominating. Studies using advanced quantum simulations show that, under such conditions, time might not flow as we experience it today. This idea aligns with theoretical predictions suggesting that time and space emerged from quantum states rather than existing independently. The quest to understand the quantum mechanics of the Big Bang continues to rely on interdisciplinary efforts. Observational astronomy, particle physics, and theoretical modeling come together to paint a more detailed picture of our universe's origins. Each discovery, from simulated quantum states to gravitational wave patterns, brings us closer to unraveling how quantum mechanics shaped the early universe. As these investigations progress, they promise to challenge our perceptions of reality itself, hinting at profound truths yet to be uncovered. The quantum dark matter. A major step forward in dark matter detection came when scientists at Fermilab and the University of Chicago used quantum tools to refine their search for dark matter. They worked with superconducting qubits placed in a specially prepared microwave cavity to enhance signals from dark matter waves. The experiment aimed to detect the faint signals that dark matter could create when it interacts with regular matter. These signals are incredibly weak and easily drowned out by background noise. To solve this, researchers cooled the system to almost absolute zero, drastically reducing thermal noise and isolating the elusive signals more effectively. The process focused on amplifying photon detection. Photons might be emitted when dark matter particles like axions interact with electromagnetic fields. Axions are one of the most promising candidates for dark matter, and detecting them could unravel mysteries about how dark matter behaves. This experiment showcased how quantum technologies such as qubits and precision cavities can transform the hunt for dark matter, opening new doors to understanding this cosmic puzzle. Alongside this, specialized devices called axion haloscopes have been developed to find these hypothetical particles. Axion haloscopes rely on magnetic fields to amplify the faint signals produced when axions interact with photons. Researchers have fine-tuned this method using quantum mechanics, increasing the chances of spotting axions, which are thought to fill the universe and account for much of its missing matter. Quantum interferometers are another innovative tool in this search. These devices measure tiny distortions in spacetime that could be caused by dark matter particles. They split light into two beams that travel separate paths, and when the beams are recombined, any shifts caused by dark matter interactions can be detected. This technique leverages quantum superposition, where light's paths behave like quantum states, enhancing sensitivity to the faintest influences of dark matter. Another candidate for dark matter is the sterile neutrino, a particle that doesn't interact through electromagnetic or strong forces, making it extremely hard to detect. Quantum experiments are paving the way to study these particles by refining neutrino detection techniques. These experiments apply quantum principles to model and potentially identify sterile neutrinos, which could offer a glimpse into the unseen components of our universe. By using quantum mechanics, researchers are exploring new avenues for finding particles that defy traditional detection methods. These discoveries point to an evolving understanding of how quantum mechanics and dark matter are deeply interconnected. Through experiments like the one at Fermilab, the development of axion haloscopes, and the use of quantum interferometers, researchers are inching closer to uncovering the true nature of dark matter. But even with these advances, much remains unknown. The interaction between quantum mechanics and dark matter is still in its early stages, and many questions remain unanswered. The current wave of research is providing a glimpse into how quantum technologies could offer the answers to some of cosmology's greatest mysteries. The next steps will involve refining these methods, expanding experiments, and pushing the boundaries of quantum mechanics further into the realm of dark matter, all while exploring new quantum candidates that might exist within the universe. As these experiments continue to unfold, they not only promise to answer key questions about the composition of the universe but also challenge our understanding of the quantum world itself. The intersection of quantum mechanics and dark matter opens up new avenues for discovery that could reshape our understanding of the cosmos. With each experiment, we come closer to solving one of the most profound mysteries of modern physics. And as these quantum techniques evolve, the future of dark matter research holds immense potential, offering the possibility of breakthroughs that could redefine what we know about the universe. Quantum stellar remnants. The potential link between axions and pulsars has ignited fresh curiosity in quantum mechanics and astrophysics. This idea opens the door to studying how these fundamental particles might interact with celestial objects like pulsars, blending theoretical predictions with observable cosmic phenomena. Axions, a strong contender for dark matter, are believed to possess properties that allow them to gather in the intense magnetic fields surrounding pulsars. These neutron stars spin rapidly and send out periodic radio waves that can be detected across vast cosmic distances. Theoretical work suggests that if axions are present, they could create unique spectral signals, providing a new way to track down these elusive particles. Pulsars offer a one-of-a-kind setting to explore quantum mechanics under extreme conditions. Their magnetic fields are 1 trillion times stronger than Earth's, and their immense gravitational pull warps spacetime itself. Within these extreme environments, axions and photons might interact, producing detectable conversion signals in pulsars' radio waves. A study published in the journal Physical Review X paved the way for observing these interactions, marking an exciting step in connecting particle physics with real-world astrophysical data. The story of pulsars begins with neutron stars, the remnants of massive stars that exploded in supernovae. These objects are incredibly dense. A sugar cube-sized piece of neutron star material would weigh as much as a mountain on Earth. In such conditions, matter transitions into exotic states dictated by quantum physics. One fascinating example is superfluidity, where particles flow seamlessly without resistance. Previously observed in ultra-cold experiments on Earth, superfluidity naturally occurs in neutron stars where superfluid neutrons and superconducting protons coexist in an environment that defies conventional physics. Superfluidity in neutron stars isn't just a theoretical marvel. It explains real astrophysical events such as pulsar glitches. These sudden changes in pulsar rotation rates have been recorded for decades and reflect quantum shifts within the star's core. By studying these glitches, scientists bridge data from space with fundamental quantum principles. This research enriches our understanding of quantum states while also shedding light on the life cycles of stars. Quasars, luminous beacons at the centers of distant galaxies, are another key to expanding our understanding of quantum mechanics. In a groundbreaking experiment in the 2020s, researchers used light from quasars to test the strange phenomenon of quantum entanglement. Quasars, powered by supermassive black holes, emit enormous energy as they pull in surrounding matter at nearly the speed of light. Their light, which has traveled billions of years to reach us, acts as a time capsule of the universe's past. Scientists use this ancient light to test quantum entanglement, a phenomenon where particles influence each other instantaneously across vast distances. This experiment not only validated quantum theory but also showcased how the cosmos itself can serve as a laboratory for exploring the universe's most fundamental principles. Entanglement suggests that two particles, once connected, remain linked regardless of the distance separating them. This principle has been tested repeatedly in laboratories, but the experiment elevated the concept to astronomical proportions by using quasar light as a source of randomization. Scientists eliminated potential local influences that might bias their results. The data affirmed the predictions of quantum mechanics, extending its validity to scales unimaginable a century ago. The experiment not only reinforced the foundational aspects of quantum theory but also highlighted how cosmic phenomena can serve as experimental tools for the smallest scales of physics. The intertwining of quasars, neutron stars, and pulsars with quantum mechanics reveals a cosmos far more interconnected than previously imagined. These celestial objects, spanning vast distances and extremes of energy, act as natural laboratories for testing the principles governing the microscopic world. Axions, superfluid states, and entanglement are not merely theoretical constructs but are actively shaping our understanding of the universe's fabric. The discoveries remind us that as we unravel the mysteries of the quantum realm, we are simultaneously unlocking the secrets of the stars. A groundbreaking experiment by Robert Wild and his team shed new light on quantum tunneling under conditions mimicking interstellar space. This study, published in March, confirmed a key principle of quantum mechanics. Particles can pass through energy barriers that classical physics says should block them. By simulating the cold, sparse environment of interstellar clouds, the researchers demonstrated how tunneling plays a crucial role in forming complex molecules in space, answering long-standing questions in theoretical physics. Quantum tunneling is also vital in the core of stars. In these extreme environments, classical physics predicts that the positive charges of protons should repel them from fusing. Yet, tunneling allows protons to temporarily overcome this barrier, enabling nuclear fusion. This process releases massive energy that powers stars and produces heavier elements, laying the foundation for the universe's chemical complexity. Without tunneling, stars like the Sun couldn't sustain the reactions that fuel them. This fusion process has shaped cosmic evolution as stars convert hydrogen into helium. They also create heavier elements like carbon and oxygen, which eventually form planets and life itself. When stars exhaust their fuel, they often explode as supernovae, scattering these elements across the galaxy to be recycled into new stars and planets. Quantum effects extend to neutron stars, the ultra-dense remnants of massive stars. These objects are so dense that a teaspoon of neutron star material could weigh billions of tons. Inside, extreme conditions give rise to phenomena like quantum superfluidity, where particles flow without resistance. Observations of pulsars, rotating neutron stars that emit beams of radiation, have linked tiny changes in their spin rates to superfluid layers inside. This behavior reveals how quantum mechanics operates even in astronomical settings. The connection between tunneling, fusion, and superfluidity shows how deeply quantum mechanics shapes the universe, from the Big Bang to the present. Quantum rules have influenced the formation of stars, galaxies, and the matter around us. Researchers are now exploring new questions. How do superfluid neutrons shape neutron stars' magnetic fields? How does tunneling function in space's coldest regions, where classical motion nearly halts? These mysteries continue to push the boundaries of science, blending the microscopic and cosmic. While quantum tunneling enables stars to shine, it also plays a role in more mysterious cosmic phenomena. For instance, in regions of space where particles encounter intense gravitational fields, such as near black holes, quantum effects could govern the behavior of matter in ways we have yet to fully grasp. It is theorized that the quantum mechanics of these extreme environments could one day provide insights into the unification of general relativity and quantum physics, two pillars of modern science that remain at odds in extreme conditions. Returning to interstellar clouds, it's worth exploring the implications of Robert Wild's 2023 experiment on the formation of complex organic molecules. These clouds are the cradles of stars and planets, but they are also where the first steps toward life may have occurred. The discovery that tunneling enables chemical reactions in these harsh conditions suggests that quantum mechanics could be a key player in the chemistry of life-building blocks. Molecules that would take millions of years to form through classical pathways may emerge more rapidly thanks to tunneling, speeding up the process of molecular evolution in these celestial nurseries. Similarly, the study of neutron stars not only illuminates the behavior of matter at extreme densities, but also holds the potential to unlock answers about the universe's most elusive particles: neutrinos. Neutrinos interact so weakly with matter that they pass through stars, planets, and even humans without obstruction. However, in the dense interior of neutron stars, quantum effects might amplify their interactions, offering a unique window into their properties. Understanding these particles better could shed light on the earliest moments of the universe when neutrinos played a crucial role in shaping the cosmic landscape. Quantum superfluidity in neutron stars also raises questions about their rotational stability. Observations of sudden changes in the spin rates of pulsars, known as glitches, suggest that the interplay between superfluid and normal matter layers could be responsible. These glitches provide a rare glimpse into the mechanics of these exotic objects, revealing the complex balance of forces at work in some of the universe's most extreme environments. Meanwhile, back on Earth, advances in laboratory techniques are helping scientists recreate some of these quantum phenomena under controlled conditions. Ultra-cold experiments that simulate interstellar temperatures have confirmed that quantum tunneling can occur even at near absolute zero. Similarly, particle accelerators are probing the fusion processes that power stars, validating the role of tunneling in nuclear reactions. These experiments not only confirm the predictions of quantum mechanics but also provide a bridge between the microcosm of quantum particles and the macrocosm of the cosmos. The universality of quantum mechanics continues to astonish scientists. From the behavior of electrons and atoms to the formation of molecules in space, from the fusion of nuclei in stars to the superfluidity of neutrons in stellar remnants, quantum rules govern phenomena across all scales. These principles, once thought to apply only to subatomic particles, are now recognized as fundamental to the structure and evolution of the universe itself. Looking ahead, the next frontier may involve direct observations of quantum effects in black hole environments or in the earliest moments of cosmic history. Theoretical studies suggest that quantum tunneling could play a role in Hawking radiation, the process by which black holes are thought to emit particles and gradually lose mass. If this radiation is ever observed, it would provide definitive evidence of quantum mechanics operating in the most extreme gravitational fields. Similarly, the study of the cosmic microwave background, the faint afterglow of the Big Bang, could reveal quantum imprints from the universe's infancy. Fluctuations in this background radiation are believed to stem from quantum processes during the first fractions of a second after the Big Bang. These imprints provide a direct connection between quantum mechanics and the large-scale structure of the universe, linking the smallest and largest scales of existence. The discoveries of tunneling, fusion, and superfluidity are just stepping stones in our quest to understand the quantum cosmos. Each finding opens new questions, suggesting that the universe is far more interconnected and governed by quantum principles than we ever imagined. As we continue to explore the mysteries of quantum mechanics, it may lead us. Quantum stellar tunneling. An interesting discovery linked quantum fluctuations to the accelerating expansion of the universe, providing a new lens for understanding its fate. Scientists uncovered that these minute fluctuations, subtle disturbances in the quantum field, could have seeded the driving force behind this expansion. This force, woven into the very fabric of space-time, influences the trajectories of galaxies, the formation of cosmic voids, and the universe's large-scale structure. This revelation ties deeply into the quantum realm, where fleeting energy changes ripple through even the emptiest stretches of space, shaping the cosmos on unimaginable scales. These quantum fluctuations, stretched during the brief but extraordinary inflationary period following the universe's birth, laid the foundation for its intricate structure. In the seconds after the Big Bang, the universe expanded exponentially, amplifying these microscopic disturbances into the density variations that later became galaxies, stars, and clusters. Observations of these primordial imprints provide a direct link between the quantum processes of the early universe and the grand cosmic architecture we see today. Such phenomena remind us that the smallest scales of existence, governed by uncertainty and wave-like probabilities, have shaped the macroscopic cosmos. Delving further into quantum mechanics' connection with the universe, theories about the energy state of spacetime have introduced the concept of vacuum transitions. These transitions suggest that the universe may not be in its most stable energy configuration. A lower energy state could exist, and through quantum processes such as tunneling, the universe might shift to this state, fundamentally altering its laws and properties. This potential transformation, though purely speculative, underscores the unpredictable and transformative power of quantum processes in determining the universe's trajectory. Recent discoveries also highlight the role of quantum phenomena in interstellar regions. Experiments conducted under conditions resembling those of the vast, frigid clouds between stars confirmed that quantum fluctuations enable reactions previously thought impossible. These reactions are crucial for forming complex organic molecules in environments where classical physics would predict stagnation. Such findings suggest that quantum effects may have accelerated the assembly of life's chemical precursors long before planets like Earth formed, extending quantum mechanics' influence to the origins of biological systems. Observations of neutron stars have revealed yet another quantum-driven aspect of the cosmos. These ultra-dense remnants of stellar explosions represent environments where the fundamental nature of matter is exposed. Layers of neutron-rich material exhibit quantum effects that defy classical descriptions, behaving in ways that influence a star's spin, heat dissipation, and magnetic fields. These discoveries help bridge the gap between the abstract mathematics of quantum theory and observable phenomena, unearthing new insights into how the universe behaves under extreme conditions. Furthermore, in the realm of cosmic inflation, recent studies have explored how quantum mechanics set the stage for the universe's expansion itself. During inflation, the universe's exponential growth magnified quantum fluctuations into macroscopic differences, which acted as the seeds of structure. These imprints provide a snapshot of quantum dynamics on a scale so vast that they are visible billions of years later in the distribution of galaxies. They also highlight the intimate connection between the random, probabilistic events of the quantum world and the organized patterns of cosmic evolution. The interplay of quantum mechanics and astrophysics opens questions about not only the past but also the universe's future. Could the accelerating expansion one day tear apart even the smallest particles, leaving a vast, cold void? Or could quantum phenomena stabilize the universe's growth, halting its expansion in ways we cannot yet predict? These questions underscore the boundless mysteries that emerge when the principles governing particles are applied to the cosmos. Quantum entanglement. A cosmic connection. The new understanding of quantum fluctuations as a driver of cosmic phenomena continues to inspire investigations into their effects across different environments. Interstellar regions, often seen as desolate, are now recognized as arenas where quantum effects dominate the formation of molecules. In these frigid spaces, chemical reactions, empowered by fleeting quantum interactions, challenge traditional views of chemical processes. These findings may explain how the building blocks of stars and planets were assembled in the early universe, providing clues to the origins of complex systems. Finally, the study of how quantum processes might influence the universe's long-term behavior raises profound questions. The dynamic balance between forces like expansion and contraction, dictated by the quantum properties of spacetime, remains a subject of intense research. Whether the universe evolves into endless growth cycles through phases or reaches an abrupt end through unknown mechanisms, its destiny is intricately linked to the quantum realm. Quantum entanglement. A cornerstone of quantum mechanics. Quantum entanglement, a cornerstone of quantum mechanics, represents one of the most intriguing phenomena in physics. It refers to a connection between particles such that the state of one particle instantly influences the state of another, regardless of the distance separating them. In the year 2024, researchers at CERN's Large Hadron Collider made a remarkable breakthrough in understanding quantum entanglement by observing it in top quarks, the heaviest known elementary particles. This discovery pushes the boundaries of quantum mechanics into high-energy particle physics, where extreme conditions often challenge the persistence of entangled states. At the heart of this discovery was an experiment conducted as part of the Compact Muon Solenoid (CMS) collaboration. Physicists demonstrated that top quarks and their antimatter counterparts could remain entangled through their spins even as they separated at velocities close to the speed of light. These particles, produced only in high-energy environments like the LHC, decay almost instantly. Yet, during their fleeting existence, the researchers observed that the particles' spin states were linked in a way that defied classical explanations. This result is groundbreaking not only because it confirmed entanglement in such heavy and unstable particles but also because it provided a glimpse into how quantum mechanics might operate at energy levels comparable to those during the early universe. Top quarks are unique in that their mass and fleeting nature demand immense precision in experimental design, making the achievement at CERN a triumph of both technology and theoretical insight. Another exciting experiment in 2024 explored entanglement in mesons, particles made of a quark and an antiquark. In a laboratory setup designed to mimic high-energy cosmic events, conducted by a team at the European Organization for Nuclear Research, CERN, this study involved colliding mesons and observing how their decay products inherited entangled properties. These observations raised questions about whether quantum entanglement in such systems could have played a role in the formation of large-scale structures in the universe. Meanwhile, an experiment in the United States focused on harnessing quantum entanglement for practical applications. At a dedicated quantum laboratory, physicists entangled pairs of heavy ions and used them to test advanced quantum communication protocols. This work has implications for space-based quantum communication systems, as it suggests the possibility of establishing entangled links over interstellar distances. Such research may one day enable the secure transmission of information between Earth and spacecraft exploring distant planets or other stars. The implications of entanglement in heavy particles extend beyond understanding quantum mechanics. They offer a way to connect the microscopic world of particles with the macroscopic realm of cosmology. Theorists suggest that the early universe may have been a web of entangled quantum states during the inflationary epoch, the period of rapid expansion immediately after the Big Bang. The observations of entangled top quarks and mesons lend credence to the idea that remnants of this entanglement might still be detectable in the cosmic radiation that pervades the universe. Another intriguing possibility arises in the context of black holes and their information paradox. Quantum entanglement plays a role in discussions about whether information falling into a black hole can ever escape, perhaps as part of Hawking radiation. Studying how entanglement evolves and decays in high-energy systems, such as those involving top quarks, could provide clues to this mystery. Could the entanglement observed in heavy particles serve as a model for understanding how black holes might preserve or destroy quantum information? Entanglement in heavy particles also enriches our understanding of quantum encryption and teleportation. While photons are the most common carriers of entanglement in current quantum technologies, heavy particles like top quarks or mesons could, in principle, offer more robust alternatives in certain scenarios. For instance, their higher mass and complex interactions might make them more resilient to certain types of environmental noise, a critical factor in ensuring the reliability of quantum communication systems. The CMS experiment at CERN also highlighted the challenges of observing entanglement in such systems. High-energy collisions generate a chaotic environment, and disentangling meaningful signals from background noise requires sophisticated detectors and algorithms. The fact that researchers succeeded in isolating evidence of entanglement speaks to the precision of modern particle physics experiments. Furthermore, the discovery opens new pathways for exploring quantum mechanics at scales previously considered unattainable. If entanglement can persist in heavy particles at such high energies, what does that reveal about the fundamental nature of reality? Could it imply that quantum phenomena are more deeply embedded in the fabric of spacetime than previously thought? As researchers continue to push the boundaries of what is observable, the implications for our understanding of the universe remain profound. The discoveries of 2024 are just the beginning. They hint at a future where quantum mechanics not only explains the behavior of the smallest particles but also illuminates the grandest cosmic structures and the deepest mysteries of the universe. The exotic quantum matter. Exotic states of matter push the boundaries of what we understand about the universe. They reveal how quantum mechanics operates in extreme environments like neutron stars, black holes, or even the early moments of the cosmos. In the year 2024, scientists have made remarkable progress in observing and studying these states of matter, bridging quantum mechanics with astrophysical phenomena. One of the most exciting discoveries this year involved Bose-Einstein condensates, an exotic state where particles act as a single quantum entity. Observed in a cosmic light vacuum aboard the International Space Station, researchers utilized ultra-cold atoms, cooled to near absolute zero in microgravity, to recreate Bose-Einstein condensates in a way unachievable on Earth. The unique conditions of space allowed the condensates to remain stable for much longer durations, offering insights into their quantum properties. These condensates are often referred to as the fifth state of matter, and their study sheds light on quantum mechanics' role in shaping matter under extreme conditions like those found near black holes or neutron stars. Neutron stars, for example, are cosmic laboratories of exotic matter. After a supernova explosion, when a massive star collapses, its core is compressed to incredible densities, creating a neutron star. Inside, the density is so high that atoms are stripped of their electrons and protons, and neutrons are squeezed together. This extreme environment creates a quantum phenomenon known as neutron degeneracy pressure, which prevents the star from collapsing further. However, deeper in the core, theorists speculate that matter may exist in even more exotic forms, such as quark-gluon plasma. Quark-gluon plasma is a state where the building blocks of matter, quarks and gluons, are no longer bound together inside particles like protons and neutrons. This plasma is believed to have existed just microseconds after the Big Bang, when the universe was unimaginably hot and dense. In the laboratory, scientists have managed to recreate quark-gluon plasma by colliding heavy ions at near-light speeds in particle accelerators like the Large Hadron Collider at CERN. However, studying this plasma in neutron stars or black holes offers a glimpse into its behavior on a cosmic scale, under gravitational forces billions of times stronger than those on Earth. Another fascinating aspect of exotic matter is its potential existence near black holes. Black holes, known for their immense gravitational pull, stretch the fabric of spacetime to its limit. Near the event horizon, the boundary beyond which nothing can escape, the conditions may allow for the creation of states of matter that defy our current understanding. One intriguing possibility is the formation of a Bose-Einstein condensate of gravitons, the hypothetical particles that mediate the force of gravity. While still a theoretical concept, studying such condensates could provide clues to a quantum theory of gravity, one of the greatest mysteries in modern physics. The early universe also provides a natural context for exotic matter. Shortly after the Big Bang, the universe was a hot, dense plasma dominated by quantum effects. As it expanded and cooled, particles began to coalesce into the building blocks of atoms. But before this, it's thought that matter existed in exotic states. For example, researchers have proposed that Bose-Einstein condensates could have played a role in the distribution of dark matter, the invisible substance that makes up most of the universe's mass. If true, understanding these condensates might help explain the structure of galaxies and the cosmic web. In 2024, advancements in observational astronomy furthered our understanding of exotic matter in the cosmos. Gravitational wave detectors have improved their sensitivity, allowing scientists to detect ripples in spacetime from neutron star mergers. These events not only emit gravitational waves but also release electromagnetic signals that provide information about the exotic matter within. The data from these mergers suggests the presence of hyperdense states of matter that challenge existing models of nuclear physics. Astrophysicists are also exploring how quantum tunneling, a process where particles pass through barriers they wouldn't normally be able to, might influence exotic matter in space. For instance, in neutron stars, quantum tunneling could allow protons to escape dense cores, altering the star's magnetic field. Similarly, quantum tunneling might play a role in the formation of strange matter, a hypothesized type of matter that could exist in neutron stars and potentially even escape into space as strangelets. If strange matter exists, it could open an entirely new chapter in understanding quantum phenomena in the cosmos. Laboratory experiments on Earth are complementing these astrophysical observations. Using ultra-cold atoms and optical traps, physicists have begun simulating the behavior of matter in extreme cosmic conditions. These simulations provide a controlled environment to test theories about how quantum mechanics influences matter in neutron stars or black holes. For instance, researchers have recreated analogs of event horizons in the lab, studying how particles behave near these boundaries. Such experiments not only validate existing theories but also generate new questions about the interplay between quantum mechanics and general relativity. The study of exotic matter also has implications for quantum technologies. For example, understanding the quantum properties of Bose-Einstein condensates could improve the precision of atomic clocks, which are critical for space navigation. Similarly, insights into quark-gluon plasma might inspire new materials with unprecedented strength or superconductivity, useful for building advanced spacecraft or space habitats. Despite the progress made, many questions remain. What happens to exotic matter if it falls into a black hole? Does it retain its quantum properties, or does it become indistinguishable from other matter? Can Bose-Einstein condensates exist on cosmic scales, influencing the evolution of galaxies or even the universe as a whole? And how do quark-gluon plasma and strange matter behave under the immense pressures and temperatures found in neutron star collisions? The answers to these questions could revolutionize our understanding of the universe, offering a deeper connection between quantum mechanics and the cosmos. The quantum measurements. The exploration of quantum mechanics and its role in understanding the universe has reached remarkable heights with a surge of interest in unconventional phenomena like quantum gravity at the Planck scale, neutron stars, and black holes. Recent breakthroughs in these areas are reshaping our grasp of the cosmos, providing fresh insights into some of the most puzzling questions about space and the quantum world. One of the most intriguing areas of study is quantum gravity, which seeks to unify quantum mechanics and general relativity. Classical physics fails to describe phenomena at the Planck scale, where space and time themselves are thought to become quantized. Researchers have made strides in theories like loop quantum gravity, which proposes that spacetime is composed of discrete loops, and string theory, which suggests that the fundamental particles are one-dimensional strings vibrating at different frequencies. Scientists used advanced simulations to visualize quantum spacetime, revealing potential connections between these theories and observable cosmic phenomena. This work is crucial for bridging the gap between the microscopic and macroscopic descriptions of the universe. Quantum effects are also being explored in the ultradense environments of neutron stars. These celestial objects, the remnants of massive stars after supernova explosions, contain matter so densely packed that quantum degeneracy pressure prevents further collapse. Recent observations of neutron stars have provided evidence of exotic quantum phases, such as quark matter, which may exist in their cores. Quantum chromodynamics, the theory describing the behavior of quarks and gluons, is essential for understanding these phases. In 2024, high-energy astrophysical observations detected unusual gamma-ray emissions from a neutron star, which researchers believe could be linked to quantum effects in its core. These findings highlight the role of quantum mechanics in shaping the properties of extreme cosmic objects. The quantum aspects of black holes are another fascinating frontier. Black holes, regions of spacetime with gravity so strong that nothing can escape, are governed by both general relativity and quantum mechanics. Hawking radiation, a theoretical prediction that black holes emit particles due to quantum effects near their event horizons, challenges the idea that information swallowed by a black hole is lost forever. This leads to the black hole information paradox, one of the most significant puzzles in modern physics. Researchers conducted innovative experiments using analog black holes in the laboratory, where quantum fluids simulated the conditions near event horizons. These experiments suggested that quantum information might escape black holes through mechanisms yet to be fully understood, providing a potential resolution to the paradox. Another key topic is quantum tunneling, a phenomenon where particles pass through energy barriers that would be insurmountable in classical physics. This effect plays a crucial role in nuclear fusion within stars, where protons overcome their mutual electrostatic repulsion to fuse and release energy. Researchers used quantum simulations to study tunneling in supernova remnants, uncovering how this phenomenon might influence the formation of heavy elements in the cosmos. Quantum tunneling also affects the behavior of particles in white dwarfs and other stellar remnants, providing a deeper understanding of their evolution. Quantum fluctuations, tiny variations in energy that occur even in empty space, have profound implications for cosmology. During the inflationary phase of the early universe, these fluctuations were magnified, seeding the formation of galaxies and large-scale structures. Recent advancements in detecting primordial gravitational waves, ripples in spacetime caused by quantum events during inflation, have shed light on these early quantum processes. Experiments using highly sensitive quantum sensors provided indirect evidence of these waves, offering a glimpse into the universe's quantum origins. These findings support the idea that quantum mechanics played a fundamental role in shaping the cosmos. Cosmic rays, high-energy particles originating from distant astrophysical sources, also exhibit quantum effects. Their interactions with quantum fields and their role in probing fundamental physics are areas of active research. Experiments using quantum detectors and space missions revealed unusual patterns in cosmic ray behavior, suggesting interactions with exotic quantum particles or fields. These discoveries open new avenues for understanding the quantum nature of the universe. Dark energy, the mysterious force driving the accelerated expansion of the universe, is another area where quantum mechanics might hold the key. Vacuum energy, a concept from quantum field theory, could explain dark energy, but its predicted magnitude is vastly different from observations. Researchers proposed a new quantum model that reconciles this discrepancy by incorporating higher dimensional effects. This model not only sheds light on dark energy but also connects it to other quantum phenomena, such as virtual particles and spacetime fluctuations. The application of quantum technologies in space exploration is rapidly expanding. Quantum sensors such as atomic clocks and magnetometers are revolutionizing the way we study the cosmos. These devices rely on the precise manipulation of quantum states and are used in navigation, gravitational wave detection, and planetary mapping. A quantum-enhanced mission detected subtle variations in Earth's magnetic field from orbit, demonstrating the potential of these technologies for future space exploration. Exotic states of matter, such as Bose-Einstein condensates and quark-gluon plasma, also play a crucial role in understanding the universe. These states, governed by quantum mechanics, occur under extreme conditions such as near absolute zero or in the aftermath of particle collisions. Experiments replicated aspects of the early universe by creating quark-gluon plasma in high-energy collisions. These studies revealed insights into the strong nuclear force and the behavior of matter under the most extreme conditions. Quantum measurements are also transforming cosmic observations. Techniques that exploit quantum mechanics enable unprecedented precision in measuring redshifts, gravitational waves, and the properties of exoplanets. A new quantum-enhanced telescope detected minute variations in starlight caused by orbiting exoplanets, providing a new method for studying distant worlds. These advancements highlight the synergy between quantum mechanics and observational astrophysics. A groundbreaking discovery reshaped how scientists view quantum spin and its role in the evolution of stars. Researchers at an advanced observatory, using ultra-sensitive instruments, detected peculiar quantum spin alignments in the remnants of a supernova. These findings suggested that quantum spin not only affects individual particles but also plays a vital role in large-scale cosmic processes such as stellar explosions and the formation of neutron stars. The concept of quantum spin is integral to quantum mechanics. Spin, an intrinsic property of particles, does not refer to physical spinning but rather to a fundamental characteristic that influences how particles behave under magnetic and gravitational forces. For decades, quantum spin was primarily studied in laboratory settings, but its cosmic implications were less understood. Recent observations, however, have unveiled its influence on stellar evolution. When a massive star approaches the end of its life, its core collapses under immense gravitational pressure, leading to a supernova explosion. This collapse is a quantum process at its core, influenced by the spins of particles within the star. Quantum degeneracy pressure, caused by particles obeying the Pauli exclusion principle, resists the collapse, but once a critical density is reached, the spin of particles determines the formation of exotic states of matter. For instance, in neutron stars, neutrons pack so tightly that quantum effects dominate their behavior, creating an ultra-dense object governed by spin-dependent interactions. Astrophysicists studying neutron stars detected unusually strong magnetic fields that seemed directly linked to the quantum spins of particles. These magnetic fields, billions of times stronger than any generated on Earth, are believed to arise from the alignment of spins in the dense neutron-rich environment. This discovery was made possible by quantum-enhanced telescopes capable of detecting faint polarization signals from distant objects, allowing researchers to trace the origins of these intense magnetic fields to quantum spin phenomena. The role of quantum spin isn't limited to the final stages of a star's life. In the earlier phases of stellar evolution, spin contributes to the generation of magnetic fields in stars like our Sun. These magnetic fields influence solar flares, coronal mass ejections, and even the stability of planetary systems. Observations from quantum magnetometers on space missions provided unprecedented insights into how spin-dependent interactions create complex magnetic phenomena in stars, connecting quantum mechanics to broader astrophysical processes. One of the most intriguing applications of quantum spin is its potential to explain the behavior of dark matter. While dark matter remains undetected directly, its gravitational effects are evident in the motion of galaxies and the bending of light. Theoretical models propose that dark matter particles might possess unique spin properties, influencing their interactions with ordinary matter. Experiments using quantum detectors searched for these elusive spin-related signals, bringing scientists closer to unraveling the nature of dark matter. Beyond individual stars and particles, quantum spin may play a role in shaping cosmic structures on a grand scale. During the early universe, quantum fluctuations in the fabric of spacetime could have included spin-dependent variations, influencing the formation of galaxies and clusters. Recent simulations incorporating quantum spin into cosmological models suggest that spin alignment in the primordial universe might have contributed to the large-scale organization of matter observed today. These models align well with data collected by space observatories, providing a new perspective on the universe's evolution. In extreme environments like black holes, quantum spin takes on even greater significance. Black holes are surrounded by accretion disks of matter spiraling inward, heated to immense temperatures. Quantum spin effects influence the dynamics of particles in these disks, affecting their trajectories and energy emissions. An international team of researchers used quantum-enhanced imaging techniques to observe spin-related phenomena near the event horizon of a black hole. These observations provided direct evidence of quantum processes operating in one of the most hostile environments in the universe. The interplay between quantum spin and gravity remains a subject of intense research. Spin is deeply connected to angular momentum, a conserved quantity in physics, and its interactions with spacetime curvature could offer insights into the nature of quantum gravity theories like loop quantum gravity. Loop quantum gravity attempts to describe how spin networks create the fabric of spacetime itself. Researchers developed quantum simulations to study these spin networks, revealing patterns that could correspond to the building blocks of spacetime. Quantum spin also has implications for the search for habitable planets. Magnetic fields generated by spin interactions protect planets from harmful cosmic radiation, creating conditions necessary for life. Observations from exoplanet missions identified several Earth-like planets with magnetic fields strong enough to shield their atmospheres. These discoveries were made possible by instruments that detect spin-related magnetic signals.